Good day to everyone. My name is Mahira, and today I'll be talking about my final year project, Traffic Analyzer and Classifier for detecting anomalies in applications in TOR browser. Okay, starting off, let's talk about what TOR browser is. TOR is an open source software built to improve the privacy of internet browsing for users and ensuring confidential communication can be established. This diagram here shows the overall design of the TOR network. It is designed to route traffic through three relays. The entry here, the intermediate, and the exit relays. The relays are chosen from about 6,000 relays that are made of a global volunteer effort. So data are encrypted several times, which will be decrypted at each relay, thus giving its name onion routing, as it resembles the layers of an onion. TOR developers claim that the network allows anonymity and improved privacy provided by the layers of encryption and onion routing techniques. However, some literatures have talked about the security problems and vulnerabilities that TOR faces. This diagram here shows the usual workflow of traffic classification process. It is used to classify or characterize traffic into applications, protocols, services, and it is used for quality of service control, intrusion detection, and anomaly detection. In this research, we focus on time-related features. The problems that we want to address is that TOR might still leave sensitive information due to the chattering laptop problem and the need for more studies on information leakage that could lead to linkability issues. Besides the possibility for the adversary to classify applications being used by the user. So what is the chattering laptop problem? The chattering laptop problem happens when sensitive information and identifying information of the user is leaked due to the failed network discovery attempts and poor use of TOR. Linkability issues happen when this information allows for the detection of the real user, their name, and other sensitive information, thus leading to our research objectives. First, we want to classify the traffic into each type of service, such as browsing, chat, P2P, streaming, and voice over internet protocol. Next, we want to distinguish between TOR and non-TOR traffic. Lastly, we wish to classify between normal and abnormal traffic. Now we look into some previous literatures related to our research. Traffic classification on non-TOR traffic, we have four important literatures. Overall, J48 or C45 was the best performing machine learning algorithm for the two papers. The first paper here used second order Markov chains and obtained 90% accuracy, while the fourth paper used deep learning and compared its results with four machine learning algorithm results. Deep learning outperformed the others and obtained 0.98 accuracy and 0.94 precision, respectively. We also have four important papers on traffic classification on TOR traffic. The first two papers obtained above 90% accuracy with decision trees and hidden Markov model. The third paper is very important to us. It compared between random forest, C4.5, and k-nearest neighbors. The fourth paper returned J48 with the best results for precision and recall. Here are the literatures related to information leak. The first paper talks about chattering laptop problem, which stemmed from the unnecessary chatter by the device while trying to discover network services at unknown locations. The second paper found that 78% of users do not use TOR properly, thus leading to piggybacking and social media vulnerabilities. The solution for this is to detect malicious exit nodes, educate users, and use HTTPS for browsing. Next, we'll go to anomaly detection. Here are some literatures for anomaly detection. The first paper uses k-means clustering algorithms to find clusters of anomalies and normal traffic. The second paper, done by Lopez et al., detected anomaly of different types of updated DDoS attacks among benign traffic. Their results show that random forest performed the best with 0.9999 on average for precision and accuracy. The third paper identified 100% of DOS attacks and more than 95% of port scans using a tool based on spectral trajectory. Let's start with our implementation. First off is the dataset generation. We generated 5 types of services traffic, being browsing, streaming, chat, P2P, voice over internet protocol. We captured it using Wireshark. Then we pre-processed the PCAP files using CIC flow meter into 5 timeout values, which are 10, 15, 30, 60, and 120 seconds. The table shows the types of services and how they were generated. This table shows the number of instances of the contents of non-TOR traffic. Here we can see the type of each type of service with their respective timeout value. Here is the same table but for TOR traffic. Next step is the features generation and selection process. From a total of 84 features, we focused on 23 features. We used selection algorithms such as subset evaluation, best first to reduce it to less than 10, and infogain ranking to reduce it to the first 15 features. Here we have the machine learning algorithms that were chosen, which are C4-5, JRIP, and random forest. The experiments were carried out in Weka and executed with their default 10-fold cross-validation. The next step is the characterization process. We'll start with the characterization of type of service for non-TOR traffic. For each classifier, we will compare the results between the subset evaluation best first and infogain ranking datasets for every flow timeout. There is a pattern here as the best performing dataset is highlighted in green and is the same dataset for each classifier, which is the 30 seconds flow timeout dataset and the infogain ranking dataset. The figure here shows the best performing flow timeout and set of features dataset for all 3 classifiers. In terms of precision, JRIP has the best average performance with the red line here. P2P returned highest precision for all classifiers, as you can see here. The figures here shows the same dataset's performance in terms of recall. Streaming returned less than encouraging results for all classifiers, as you can see here. As you can see here, while browsing had the best performance for all classifiers. We will continue with the second experiment, which is the characterization of type of service in TOR traffic. We repeated the same steps as before, similar to the previous experiment. Infogain ranking returned the best results, however this time with the 10 seconds flow timeout dataset. The figure here shows the best performing flow timeout and set of features dataset in terms of precision. Highest precision is obtained by random forest for browsing. It's in the brown line here, while the lowest precision is by C4-5 for voice over internet protocol in orange, as you can see here. Here, the figure shows the same dataset's performance in terms of recall. Both C4-5 and random forest performed similarly on average, the orange and the brown line, The highest recall value is by C45 for browsing in yellow here, while JRIP has the lowest recall value in red for overall in average. Next is the third experiment, in which we will conduct characterization between TOR and non-TOR traffic. Similar to the last two experiments, InfoGain ranking outshines subset evaluation best first dataset. The second table here shows the true positive rate and the false positive rate of InfoGain and ranking datasets for both C45 and k-nearest neighbors classifiers. The latter returned better results for all precision, recall, true positive rates, and false positive rates, although the differences are not very significant. Here is our last experiment, which is to classify the anomaly. We matched the experiment done by Lopez et al. And tested out with C45 classifier. We used the same dataset, which is the CIC-IGS17, but we could not truly replicate it due to the big size of the datasets. Our experiments showed that C45 returned really good results with 0.9999 precision and recall with high true positive rates and low false positive rates as seen in the table here. Now, let's talk about what the results mean. To benchmark the results with previous literatures would be unfair. However, we would like to make some sort of comparison on how different and similar the results turned out. For characterization of services, Lashkari et al. Stated that 50 seconds would be the ideal flow timeout value for the best results. This was not the case with our results, as we obtained the best results with 30 seconds dataset for non-TOR traffic and 10-second dataset for TOR traffic. But similar to their paper, on average, Random Forest performed the best among the other three. For characterization between TOR and non-TOR traffic, we distinguished between TOR and non-TOR traffic by using machine learning algorithms such as C45 and KNN. Different to Lashkari et al.'s work, KNN returned better results than C45 for our dataset. KNN was able to detect 99.9% of all the non-TOR samples with 99.7% precision, while 86% of the TOR samples with a success probability of 92.9%. As for anomaly classification, C45 classifier returned 0.9999 weighted average for both precision and recall with very low false positive rates, which can be compared to the results of previous works done with random forests. We generally compared the results, but as it is not the best comparison, we want to do more research by truly comparing the classifier results with previous literature. Here we can see that the TOR traffic can be classified and characterized to the type of services being used, thus allowing the adversary to find any affiliations with the real user. To conclude our paper, we will be revisiting our objectives and the results. Our first objective, to classify non-TOR and TOR traffic into its type of traffic. The results, we were able to classify both TOR and non-TOR traffic into browsing, chat, P2P, streaming, and voice over internet protocol with relatively high accuracy from all three classifiers. However, Random Forest returned the best results for both TOR and non-TOR traffic, which is in line with the previous literature. Our second objective is to distinguish between non-TOR traffic and TOR traffic using machine learning classifiers. By using C45 and KNN classifiers, we were able to classify between TOR and non-TOR traffic with relatively high precision, recall, and true positive rates. Our third objective is to investigate whether the abnormal traffic are traffic that leak any sort of information on its users. Resources for TOR datasets are scarce, and that it was difficult for us to replicate an attack on TOR. However, we were able to collect some insight. Information leak is especially probable at the TOR exit relay if communications are not encrypted or if fingerprinting attacks are done. However, it is possible to detect the anomaly with high precision and recall by using random forest and C45 classifiers. Anomalies detected could easily leak information to the adversary. Thus conclude our research project. Thank you for your time.